This is Professor Jimenez, and we're going to start today with the programmable timer or programmable time delay. So using the PIC 1619, we will apply here code on port B, where we have the inputs RB4, RB5, RB6, and RB7. Where RB4 will be the least significant bit and RB7 the most significant bit. In this case, with this deep switch, we will select the time delayed in seconds to generate a pulse right here to turn on this LED for the time preset by these inputs. The binary weight for the least significant bit for RB4 is 1. So these are the binary weights, 1, 2, 4, 8. Well, right here, this one represents the P numbers, but the binary weight is 1, 2, 4, 8. So the maximum number we can reach is 15. So this is the range of this timer, which can operate within the range of 1 to 15 seconds. And we will use some of the previous software that we use to generate these pulses, the 1 second pulses. Well, the timer will, when you press this push button, it'll start a sequence. If the code here is 0, there will be no output. If the code here in binary code is different from 0, then you will see here an output. So the time delays that we tested in the scope, for example, for 15 seconds, we can see it here. 15 seconds. When we press the switch, you get this time delay, 15.083 seconds, so very accurate. And also for 14 seconds, and of course the minimum we can reach is 1 second. So now that we have the micro where we are using RA3 as our input for push button, RB4 to RB7 for the programmable time delay, and RC0 will be our output. So we can see that we are using 3 ports, but you can see here something very important, that the binary weights do not correspond to RB0, 1, 2, 3, because those pins do not exist in this micro. So notice that these positions are not in the right binary weight. So we have to shift these 4, or we have to swap them, these 4 bits, or this nibble, we have to swap it and put it in the correct positions in another register or in the accumulator, so that the numbers here have the correct binary weight of 1, 2, 4, 8. Because as you can see here, the binary weight will be we have 1, 2, 4, 8 will be 16, 32, 64, 128, and we don't want those binary weights. This is why we have to move them or swap them to the correct position. So to start with the code, we start writing the code, and move this a little bit. So we start by configuring the ports, configuring or setting the configuration word. We saw another video explaining these details, and now we declare these variables. K1 is a variable byte in this location, hexadecimal 20 in the round memory. K2 is another variable byte. K3, it will be in this location. T for time, T will be another variable which will be in location hexadecimal 23, and R it's a variable byte that we have here. I think we're not using this one, but even if you don't use it and you declare it, that's not a problem. Okay. Now we have the assembler instruction, the ASM. This instruction indicates that the next set of instructions from here and below, all the instructions are in assembler code. Now we have the start label. This is a label that we are assigning a name. Every time you declare a label, you have to use the column. So we select bank 1 to configure the micro, because that's the first thing we have to do. We have to configure our ports. So we know on port 8 we are moving, we go to bank 1, we move these constants, and then we move 255, so all ones to try say that to indicate that port A is an input, and also port B, all those files are an input. Notice that when you have here 255, which is equal to all ones in binary code. Let me put it here. There is in binary. So this is a least significant bit, and this is a most significant bit. But notice that when you move this byte, this whole byte to, let me put it in yellow, when you move it from W, because now it is in W takes this value, move 255 to W, so this binary code goes to W. Okay, so when we move the contents of W, all ones, to trace B, okay, and we know that in trace B, these bits do not exist. Okay, so that is not a problem. The only bits that are implemented in the micro will be transfer, which are the most significant bits. Okay, from RB4 through RB7. Okay, so and then because port C is an output, we clear try C with this instruction, clear file try C. Okay, so all pins in port C are outputs. Then we control the internal resistors, the pull-up resistors, because we don't want the pins to float. Which pins? These pins. These pins, if you don't place the internal resistors, the pull-up resistors to voltage, the pins will be floating when the switch is open. And if they are floating, you cannot determine if it is a 0 or a 1. That will create a problem. So that's why we have to place the internal pull-up resistors on port B. And this is done with this instruction. Okay, the bit set equal bit set file from this file, we pull up on port B, bit 7, make it equal to 1, and that way we will have we can transfer the contents FF to W, and we transfer those to port B and port A. That way all pull-ups in ports A and B will be enabled, but in port C they will be disabled because port C is an output. When you have outputs, you don't need pull-up resistors. Okay, now we select bank 0, and with bank 0 selected right here, we clear all ports, clear file port A, port B, port C, to make sure we don't have any data there. Now we start the code right here. Okay, and this is where things start getting interesting. And we have the instruction, the first label state, and right here we have bit clear port Z.0. So we clear port C.0 where the LED is connected. So we're just making sure that the LED is off. Okay, the LED on RC0. Now we do a very interesting instruction here, the instruction swap nibbles on port B and store the contents on W. That's why there is a 0. Okay, let me highlight that one. So what is happening there? So we are reading port and swapping nibbles. So nibbles RB4 through RB7, they take positions RB0 through RB3, and RB3 to RB0, they go to these positions. So it is a swap. And what happens in that instruction, let me clarify it a little bit, is right here. As you can see here, we have the swap, and in this instruction right here, we can see that this instruction swaps swap nibbles in any file. So this is the operation file. In any file, bits 0 to 3 go to bits 4 and 7, and bits 4 to 7 go to bits 0 and 3. So that's a swap. And this is the description. The upper and lower nibbles of register F are exchanged. If D is 0, okay, this D, the destination, if D is 0, the result is placed in the W register. Okay, and that's what we're doing. We are putting the result in the W register. So we are reading port B by doing that. So let me go back to the code, and you can see here that now when I am doing this, W move swap F port B, this is a file, swap F 0. This is the file, and the file is port B. So we are reading port B and swap nibbles because the contents are transferred to W. So the contents of port B, once they are swapped, are transferred to W. This is how we read port B. Now the contents are the port contents or port B contents are in W, and from W we transfer those to a variable called T for time. Okay, and this is done with the instruction move the contents of W to file T. We are using the underscore T because this was declared as a variable in the beginning. It was declared as a variable in one of the locations of the memory, RAM memory location. So every time we declare it in the beginning, we have to use the underscore. But if you are using the file number here, you don't need the underscore. So what happens is that the contents of W are transferred to T. And I place this because the X means don't care. So we don't have any contents on the most significant bits now. And we transfer by doing the swap. Bits 7 through bit 4 are now in the correct positions. Which of course we understand that bit 4 is now the least significant bit. Okay, in this new variable, this will be bit 0, bit 1, bit 2, bit 3. But now they have the correct binary weight. That's why it is important to do the swap to get the correct binary weight in the variable time. Okay, now we move. So this is transferred to T, and now we move T, 1. Why are we doing this? When you move the contents of a variable to the same file, to the same variable, F to F, file, move the contents of this file to this file, and because if the contents of this variable T are equal to 0, okay, then the bit Z is equal to 1. This bit comes from the arithmetic logic unit, which tells you that after doing this transfer, if the file is equal to 0, this bit will be 1. But if the file is different from 0, this bit Z will be 0. Okay, and and that's the way to do it. But how we're not testing Z yet. The micro in the arithmetic logic unit in this bit Z, the Z bit, which is located in the status register, this bit is telling us what happened after doing this transfer. So it is a very powerful instruction. Okay, moving the contents of one file to the same file, it's a powerful instruction. You might think there's no reason to do this. Yeah, there is a reason, and it is to determine if the contents are equal to 0 or not. Now, how do we test the Z bit? By doing this bit test file. Which bit? Bit 2, and bit 2 is the Z bit in the status register, to determine if this bit is equal to 0. So skip it clear. So if that bit is equal to 0, that you have to go here, skip it clear. So skip this one and go here. But if Z is equal to 1, jump to this instruction. So there are two ways to jump, here or here. And if the code jumps here, where Z is equal to 1, that means T is equal to 0. So time is equal to 0. So the user has all the switches on port B grounded. Okay, switch it to ground. So there is a 0, and you don't want any time to happen on the output. So this is why it goes back to state, waiting for the user to change that number at any time. Okay, once if the t variable is different from 0, now the code, when it is testing the Z bit, because right here the code is testing Z. So what is the status of Z? Right here. Let's go back there. So it's doing, what is the status of Z? So C equal to what? 0 or 1? So that's what this instruction is doing. Okay, and so if Z is equal to 0, that means that time T is different from 0. So it jumps right here, and now we have to test right here if the user is pressing the push button to start a time sequence, or a time sequence. So we have to test port A3 or RA3. So is RA3 equal to 0? If it's equal to 0, if R3 is equal to 1, okay, go to state, go back. That means the user has not pressed the push button. If the user presses the push button, then it'll be here, bit test file, skip it clear. So if it is 0, skip this one and go here. So now the user pressed the push button to turn on the LED, and we turn on the LED with this instruction, bit set. Which bit? Bit 0 from this port, turn it on, or bit set. So port C, that 0 is equal to 1. Now the LED is on. But then our next step will be calling this subroutine, okay, which is called seconds pause, okay, or 1 second pause. So we call the subroutine 1 second pause, which is this label. It is right here with this right there, with this column indicating this is a method. So when you see the instruction call sec pause, it is invoking this method or this subroutine. So this subroutine starts by loading constants to K1, loading and storing this number 6 on constant K1, then clear W. Now we move another constant to 136, and we do the loop. This is another code that we saw in this class, a previous code for 1 second delay. So now we are using it as a method. And we start loading K2, K3, and then we start a series of decrements. So nested loops. And then we start decrementing K3, go to T1. So we start with this loop, nested into this loop in green, then nested into the blue label into another loop. Once these loops are finished, we have 1 second. So we return right there from the calling instruction. And where do we return? We have to return to the very next instruction because we were calling. We return to the very next instruction, which is this one. Now we decrement time delay variable t. Okay, we decremented by 1 because if the user selected 1 second, so we decremented, then we have to test it. Decrement T1 and is skip is 0. So if it is 0, go to state, start another sequence. But if it is not 0, if it is different from 0, go to rep. So do this process again, call it again, because the user had a number different from 1. For example, if he had pressed enter number 3 on port B, so this variable starts number 3. So you have to decrement it 3 times, and that way you will call three times this method, and you will have the 3 seconds that you needed. Okay, once t is equal to 0, it goes to stay, and that's where the code that's the beginning of the code again. So the micro will be here reading ports and waiting for the user to press the push button, okay, and testing if the result, if t is equal to 0, as I explained before. So that's where the code ends, and this is all for this code, and you can make another change. So one assignment that I will be giving to all of you watching this video is, if this method was for seconds, so right here we were selecting seconds, okay? Now the new code I need is milliseconds, so in such a way that I can program here from 0 to 15 milliseconds. Okay, from 0 to 15 milliseconds. So right here you have the binary weight 1248, and you can get time delays here from 0 or from 1 to 15 milliseconds, not seconds as we did it in this code. So that'll be your assignment, and I will give you more details about the due date in our groups. Thank you. That's all. Thank you. Bye.